So I thought we could work with the DIA data again, the tutorial data that you did with the written tutorial. But how many people did people have all the data? Do you have both the TTOF and the QE data, or did people? Okay, so what? People who only have one, what do you have? QE. Okay, I guess we'll use QE. I haven't done this with the QE, but we can certainly do it. Yeah, let me just quickly. So, is anybody here? Did anybody here do the tutorial with the triple TOF? No. Okay, so it's all QE, which I have. The other thing that we're going to need is we're going to need Skyline Daily. How many people have Skyline Daily installed? Okay, so if you don't have Skyline Daily installed, let's see, is mine up to date? No. So I'm gonna update mine, or maybe I'll just for the person who doesn't have it, I'll update it from the website. So if you don't have Skyline Daily, you got to go to the website and go to the installation page. So if you're anywhere else in the website, you can click on the little Skyline logo and then click here, and then click Skyline Daily Beta button there. And that will bring you to the Skyline Daily page. Should. And then you click I agree and install Skyline Daily, which gives you the setup. And if you click that, you should install pretty quickly. All right, so hopefully people can generally get to here. And then, so there are wizards that you can start from on here. One thing I want to do before, we're going to actually use a wizard to process this DIA data. But before we do that, the wizard, I just taught this at ETH in Zurich, and we realized that there are a couple of values that don't get set in the wizard. So I'm going to have everybody just go click through blank document again. And go to start with settings default again. Is everybody have this installed? And you got it installed, okay. How about in the way back? Are you installed and done? Do you have Skyline Daily? So the other, you know, the easiest way to tell whether you're running Skyline Daily is that there's a little red arrow Skyline logo for Skyline Daily. So if you don't have sort of red up in the corner of your, and you're not running Skyline Daily, you can also go help about, and that will tell you that you're running Skyline Daily 4.11, etc. So everybody should click settings default, and no, don't save your old settings unless you want to. And then we'll go ahead and turn on integrate all. And then the one important setting that is missing that I'm working on adding is to go to transition settings, instrument, and here we're going to use minimum MZ 300 to 2000. And then click OK. And now we can I guess we could click on the start page, you know, file start. Do you want to save changes? I guess we do. Yeah, so let's save what we've done to DIA, you know, wherever your QE directory is. let's call it DIA Skyjam. Everybody with me? Good, okay. Save. So then we come into the start page, and what we want to do is the import DIA peptide search. This wizard. And we're going to build a new library from the DDA data, just the way you did yesterday. Except this wizard's going to take us all the way through it. And we need to choose a cutoff score. And in this case, 0.95 is fine. At the DIA swath course, they taught us how to come up with what the right for this cutoff score. It's not an FDR based score. It's called a posterior error probability, and it's generated by peptide profit in the case of the data that we're working with, and so it just means that at that point there's a 1 in 20 chance that it's a false discovery, but we don't really know what the false discovery rate is. I think the 1% false discovery rate actually required you to have like a 97 cutoff, but we'll just leave it at 95. It's going to be fine. And then click Add Files. And if you go into DDA search, you can just pick this Interact PepXML. So this is sort of leading you through steps you did in the tutorial. Eventually, we'll probably change the tutorial to just use this wizard, but we made this wizard better so that it can just do the whole workflow in the wizard. And then we just tell Skyline that we have the diagnosis 11 IRTs, and does anybody know what an ambiguous match is? It doesn't tell us if we. I'm surprised there's no tip here. So an ambiguous match is when the search engine, a peptide search engine, just says that a spectrum might be for multiple peptides, and we're not going to include those. So we'll get a message telling us how many ambiguous matches were in the data. Everybody here? So click OK, or click Next. And then Skyline's going to start building the spectral library. It's reading spectra out of these MZ-XML files. It read the search results out of the PepXML file. And now it's doing this. Skyline creates a redundant library that has all the matches, and then it creates a non-redundant library which has the best match for everything. And then now it tells us that it was able to, it found the IRT peptides in our data, and yesterday, I think when we did this, we got because this library is built out of 2 files, so we got 2 rows here. The reason we only get 1 row here is that I found that you get better IRTs if you have a bunch of runs. You get better IRTs if you align all the runs to each other, and then calculate the IRTs based on that alignment, than if you simply use the 11 points to align them all. So internally we build the blib file, and then we take all the runs, and they have they share thousands of points, and then we do a regression based on that, and then we finally map everything into IRT space. So you can click and see the regression for the IRT peptides, and it found all 7 and used them. So that looks good. We have an R of actually 1.0, so quite good correlation. And then now it asks us, do we want to recalibrate the IRT standard relative to the peptides being added? And in this case, we're doing a very limited experiment where I'm not intending to share these IRTs with anybody. And just like Brian was explaining that if you did sort of on-column alignment in DIA, when you did a DIA experiment, if you ran some things on the same column and then you could create a chromatogram library, similarly, I think these samples were all run on the same instrument. And so aligning the IRT standards again, they'll be close to the values that Biognosis originally assigned, but they'll be better for us. So we're going to click yes in this case. And now we need to, you're going to work with some DDA data today and extract MS1 chromatograms, but in this case, the DDA data and the DIA data are 2 separate things, right? So somebody a little bit, whoa, wait an hour. Yeah. A little bit like Brian was saying, we are now using DIA runs to then go search DIA runs, but these are DDA runs that were created on pooled sample, and then we're going to use them to search DIA runs. So we have to tell Skyline where the DIA runs are. So click the Browse button, and now go to the DIA folder and choose the 6 DIA files. And click Open. Now we'll just put all those in there. And then otherwise we can just leave the files simultaneously at whatever you had before and click Next. And now it says it wants to remove some things. That's probably fine. Maybe we might get rid of the, keep the 170 so that we know the run. Yeah, or I guess we could also even keep 1803, which will tells us the date, right? It was March 2018 when these were collected. So you can keep or remove as much as you want at this point. Click OK. And in this case, we're going to go ahead and allow charge 4 precursors, just like yesterday. We're going to have Y, B, and P ions. We're going to have this is a high, this is a high accuracy ion match tolerance. So this is about 50 ppm, which is fine because this is all collected on Orbitrap. And we can go ahead and say exclude DI, use the DI exclusion, and then we're going to use 6 product ions, minimum 6 product ions. So we're going to ask for 6 product ions, and we're going to exclude anything that doesn't have 6 product ions. And this is just the standard from the original swath paper. Seems to work pretty well. You could choose, certainly there's some flexibility here. You could choose a minimum of 4, or you could choose to try to have 8 or whatever. So, but these are the settings we're going to use. They're pretty good defaults. And click Next. And here we have, so count of the precursor peaks. I've tested these data, and 10 ppm mass accuracy works fine, even though in the tutorial, either anywhere between 10 and 20 work fine here. We'll stick with 10. So it turns out I've done a fair amount of looking, and what I've looked at, if your mass spectrometer is well calibrated, and you're using either SciX, a modern SciX, or an Orbitrap, or a Bruker instrument, Bruker TOF. Those are the three that I've worked with, and 10 ppm works pretty nicely. So I didn't do, well, maybe nobody did this yesterday on Skyline Daily. So you may not have the isolation scheme in here. So let's go ahead and rebuild the isolation scheme. You'll remember this if you did this yesterday. So so we're definitely doing DIA, centroided 10 ppm is all good. And now we need to just add the isolation scheme, which is going to be a pre-specified window isolation scheme. And if we had raw data, we could just tell Skyline to import it. But unfortunately, all we have is MZXML files. So in the tutorial we just did at ETH, we actually included a raw data file so that everybody could use this import button. But in this case, we've got to just paste it in here. We're going to have a margin, so click check specify margin. And now we've got to go to the file system and is it, I think, in the DIA folder? Yeah, 18 var TSV. So I guess open that in a text editor, Notepad, or whatever you like, and then you have to copy those 19 lines, right? It's actually 19. Okay, so copy. Do people have that? Anybody need more time? Okay. Once you have that little block of text copied with, into the clipboard, then you can just switch back here and click there and then Control V to paste. And that will give you your 19 windows. And then to just yeah. The measurement dropdown is not showing up. Oh, you didn't click, and you didn't click specify margin, because it's really dependent on specify margin. So if you're not specifying a margin, then the measurement and the extraction windows are the same. It's only when you're specifying a margin that and so if you want to see what that means, is like you can say extraction, and now you'll see that, it's 401 to 429, 429 to 458. So you can see the extraction windows don't overlap. The measurement windows are what you actually tell the mass spectrometer, right? So you tell the mass spectrometer, hey, measure 400 to 430, 428 to 459. So you can see they have a little bit of overlap. If we click the graph and make this pretty big, then you can see the margins. And so if they overlap when you include the margins, and when you drop the margins, they don't overlap. So that's what we're aiming for, and that was explained yesterday. So everybody has this. We can just call this QE 19 var or something like that, and click OK. So, and Skyline automatically chooses to use this. We're going to use scans based on predicted retention time, and 5 minutes is fine as a window at this point. Everybody ready? Click next. Okay, so now we have to tell Skyline what the targets are. We can choose to allow for 2 miscleavages, and let's click browse, and we're going to use this full N Prado 3 mixed human yeast E. coli. So we're setting things up to do a discovery experiment inside Skyline. We're just going to use the entire proteome FASTA file. This actually includes the IRT peptides and the reversed proteins too. So click open. And then we're going to do, we're telling Skyline to build, we're going to tell Skyline to build a model for us. And so we need to also tell it how to generate decoys. So we'll go with shuffle sequence. And then we get a chance to say how many decoys per target. The default is 1. If you have a very large library, and you're going to get, like with the pan-human library, I was tending to use about, I would use a factor of like 0.2, because you don't need, the way the decoy modeling works, in theory, it shouldn't really matter what percentage you use. You're just taking a sampling. In practice, I found that I got slightly fewer detections with 0.2 than with 1. And then I even went all the way up to like, I'm gonna have 6 decoys per peptide, and that didn't really help either. But it didn't really hurt. It was in neither direction. You had to get pretty low, like to 0.1 for the pan-human library before things really started to fall off. And that's just an indication that the model doesn't work as well eventually. But we'll just stay with 1, which is the default. And then we want to tell Skyline to just automatically train an nProfit model for us. So now we've gone through this wizard. Somebody was talking about it's really, really daunting to just walk up to Skyline and see the blank document. There are several wizards like this this will take you through everything you did through a bunch of different steps in the tutorial. And then, so if everybody's here, anybody miss a step or get stuck? Okay, then click finish. And first, Skyline is now going through the FASTA file, which is a pretty sizable FASTA file. So I think probably in the past you've seen when you're adding FASTA, it's pretty instant. In this case, it takes a while to get through the whole FASTA file, digest it, and even allow for 2 miscleavages and check it against the library that you built. And then Skyline will finish up and add a bunch of new targets to our document. Oh, actually, first it will tell us what it's adding. So it says, okay, there's 4,148 proteins, 35,000 peptides, 38,000 precursors, 346,000 transitions, and this is all, I think that the following targets. Yeah, I don't quite know whether that includes decoys or not, or whether that's just targets. So maybe that's just targets. We could do things like we could say, yeah, I'm not going to trust anything that doesn't have at least 2 peptides per protein. And Skyline will recalculate and say, okay, that gets rid of, you can see that a lot of our peptides, a lot of our proteins are only represented by a single peptide because we drop by, 1,500 proteins. So let's leave that for now. Another thing we definitely want to do is, think about something with duplicates. And I would say in this case, we're just going to remove duplicates. And then you'll see that, 600 of our proteins and 600 of our proteins, 8,000 of our peptides, or 7,000 of our peptides were duplicates. So, we definitely want to remove those. And that gets us down to 271,000 transitions. So about 250,000 transitions. Click OK. That's all we're going to do, but we could certainly make more, apply more limits. And then now Skyline puts all of that into our targets list, and you can actually see it showing up in the status bar down here. Status bar says we have 3,485 proteins, and then 27,670 peptides, which is now going to include the decoys. So if you scroll down to the bottom, you can see decoys at the bottom. Up at the top, we have our IRTs. So if you click on IRTs, well, things are getting imported at this point. I'm going to hide this. So it's fun to watch the data import. Somebody once said it's so much fun. It's so great. You feel like you're doing work even when you're just sitting there watching it. So click hide for the moment. We can always get it back. The progress continues down here and actually shows up in the taskbar as well. So in order to get a false discovery assessment, you can see that as I scroll through here, I've got some proteins that say reversed at the beginning. There are a couple. What I like to do is go edit, refine, sort proteins by name. So edit, refine, sort proteins by name. Does that work? So, and then you can see that there are some reverse proteins up at the top. And what I will do is just put my cursor on the first not reverse protein. And that gives me a quick decoy counting way of assessing false discovery rate. So I can say, 66 out of 3,500 is roughly 2%. So at a protein level, I have a 2% false discovery rate here, but at a peptide level, I have way less than 1%, right? So depending on how you feel about that, if I had done something like, if I hadn't accepted proteins with just one peptide, I would have a minuscule false discovery rate, because if you expand some of these, you'll see that most of these peptides have only one. Most of these proteins, these reverse proteins, have only one peptide, and that's sort of the nature of false discovery proteins. All right, so then I can click this button here, the chromatogram button, see how it's going. I guess this is gonna take a little bit longer than what you did yesterday when you were only trying to get chromatograms for 18 proteins, but it shouldn't be too terrible. How are people doing? Is anybody as far as me, or raise your hand if you're close to where I am, which is almost done with. Okay. So this is a little bit dependent on, also, if I bring up the task manager, it's a little bit dependent on memory. So if your computer, so you can see Skyline is using up most of my CPU right now. It's not anywhere near my memory. I think at this point, if you had 8 gigabytes of memory, you'd be fine. I have 16. And I can switch to performance here and look at the CPU and look at the memory. And if you do this and you look at the memory, and the memory is ever like pegged up here, then who knows how long it will take, because Skyline's having to swap things to disk. And it may, something that would take a minute or two when your memory is not pegged might take an hour. And that's just because the operating system is struggling to try to get memory. So in general, when you're doing these large-scale DIA experiments, you wanna make sure that you're well below your memory limit, and then everything will go smoothly, and Skyline will have no problem using up as much CPU as you'll allow it. And so now, at this point, you can see that in my first two files, Skyline has finished the chromatogram extraction, and then this last 13% is it's just scoring peaks and picking the peaks in the chromatograms, which there are a lot of, so that will take a little time. So I can hide this again, and then ask to view peak areas, replicate comparison. I generally like to have these windows up, peak area, and then retention time replicate comparison. So bring those two windows up, and if I don't have a whole lot of them, like yesterday when we had 42 for the rats, I dock them at the bottom, but mostly if I don't have a lot of them, I'll dock these two windows over to the right. And now as the peaks and the data come in, they'll start to show up over on these graphs. I'm gonna bring it back up again. 95%. It's getting close. So there are my first two. And I think if I select IRT here, so select the IRT peptides, and I'm going to hide this again. Now I see one of them. I should see the second one in a moment. So there you go. So I've gotten through two of them. Has anybody else made it through two? Yeah? Okay. Take a little bit more time for the rest. So I guess we could go to view, playing with fire here, I think, but let's try it. View document grid. Oh, actually, yeah. And now if we go to replicates, so I don't have the annotations that we want here. We want to have a condition annotation at least. I don't know that we need a bioreplicate one unless we're going to be working with MS Stats. So let's go to settings, document settings, and if you have a condition field, well, I should probably take a look at it, see what it's got in there. Edit list, edit. And so it's just a text value that applies to replicates. Do people have condition? Okay, so if you don't have condition, click edit list and add it. And if you do, just check to make sure that it's we're just going to leave it text. It doesn't need to be a value list. We've been using a value list, but that doesn't need to be the case. So everybody got that? Click OK. And then the condition should show up. I clearly have group by condition on because as soon as I added the condition value, it reduced me down to one peak area and one retention time. So I'm going to right click here and turn on, so group by replicate, go back to replicate view. And now I'm going to label my conditions, which are just A, enter, B, enter, A, enter, B, enter, A, enter, B, enter. Already got that? So I'll bring up my little progress window here. And I'm about 75% through the next two. So you can do large-scale discovery DIA in Skyline. It works pretty well. You know, works better if you have a faster, more powerful computer. We do a fair amount of it on a modern development computer, which is it's pretty easy. For under $2,000, you can now get it looks like you can get a hex core. So they finally, the i7, we were getting quad core computers for a really long time. It looks like it's not that hard to get something with 6 core in it. And then we can, it's not very expensive to get a 64 gigabyte machine with 64 gigabyte of RAM. So that would be a great computer for doing this kind of stuff. We also have a computer in the lab. It's a shared server that's got 24 cores and like 178 gigabytes of RAM. So those kinds of machines are out there too, and more and more people are using them for these really large scale experiments. Has everybody made it? Everybody who's following along, has everybody made it through at least 2? Is there anybody who hasn't made it through the first 2? You haven't made it through the first 2? Ah, you got an underpowered laptop. Let me see how far you are. 93%. Okay. What's your, so bring up your task. Okay, go back and watch your thoughts. It's my personal. Oh, it's your personal one. Yeah, well, I like this this ThinkPad here. In Barcelona, my other computer died, and I got to use Mike's ThinkPad, and I was like, "Oh, I got to get one of these." But has anybody made it through 2 through 4? No. Well, I'm pretty confident that I'm gonna at least make it through all 6 before we have the break here. The nice thing about in Zurich, they use virtual machines, so everybody's just like remoting into a virtual machine. Oh, yeah, here's Rudy. Yeah, so they have this amazing lecture hall, and everybody's on virtual machines, and so everybody finishes at exactly the same time because are basically all in replicated systems. So I'm on number 5, number 6 maybe soon here. All right, so I'm going to hide these again. Anybody else made it through 4? Okay. In the retention time plot, I think this is pretty good, but like, I mean, everything seems to be lining up quite nicely. But one of the reasons I made it so that you could have a line plot here is because I think it's easiest to look at. Do all of these peptides line up if there's a line connecting them? So you can right click and choose value retention time, and then now you get these lines, and you go, okay, great, my IRTs look good. They're all, there's not anything sort of jumping around. Our expectation for IRTs is that ideally they go straight across, but otherwise they sort of all should move together. And then what's our expectation of the IRT peptides in peak area? Well, my original expectation was that they should all be straight across too, right? They're all injected they're supposed to be injected at the same concentration. So I got pretty surprised that wasn't the case. Here you can actually kind of see a pattern. And then you can also order by your condition. And we don't have the third value yet, but I think it's pretty interesting that condition B seems to have a higher amount of them. So that makes me wonder about the sample handling. Although definitely these, some of these peptides are not totally stable. They're like, so this one, most of them are pretty consistent, but this one seems to be moving around a bit. And I think I can maybe click on this bottom point. Did I get it? No. I might have to zoom. So this one that's moving around a bit seems to be this second GAGs peptide. So it seems to maybe be a little bit less stable in its peak area. And you can also have a look at that. You could, I'm going to hide the document view. You could go through each peptide one by one. I think we mentioned this yesterday. This sort of dropouts here. They indicate that I might not have gotten the extraction window right. So this is centroided data, and when your extraction window isn't wide enough, centroided data will just like disappear like that. So when you see otherwise pretty smooth peaks and they have dropouts like that, that means that you might want to think about widening the window. So for the most part, that we don't see that, but we see a little bit, and so that might indicate we would want to go back and re-extract with like a 15 ppm window. We could start to think about, I think even, at this point, I don't have all the data in, but I could start to take a look at view mass errors histogram just to get a sense of that. Oh, mass error is unavailable. Oh. Why not? Huh. I guess it's not, I don't know why it's not giving me the mass errors. Maybe it has to finish. I can also right click here and choose split graph. Did you guys do this yesterday? And then that will show me that, you know, it's really maybe it's only my precursor isolation window that needs to be a little bit wider. But mostly I don't see that problem. All right, I'm going to pop up the window here again. I'm at 90% on my last two. It's taken me about 20 minutes. Where are you? You haven't done, yeah. What kind of computer do you have? An ancient Mac. Oh, that's embarrassing, huh? Okay. So yeah, now when anybody says, "Can you use Skyline on a Mac?" I'll be like, "Yeah, even really old ones." Okay, so. All right, so mine's done. Well, it's joining, but I've got all the values, and in a moment it's gonna. So now you can see the progress. If I close this window, my progress is now it's building the mProfit model. And then it's actually applying the mProfit model. And now it's going to show me the mProfit model. In a second. And there it is. So this is the mProfit model for the complete. So most of these little negatives don't mean anything. They just mean that signal to noise, product mass error, and product precursor shape were not useful. The precursor isotope dot product actually is a pretty useful score. You can see it's accounting for 24%. Library dot product is always an important score. Retention time difference, that sort of tells me how good my IRTs are. There's a little bit there. We have retention time difference and retention time difference squared, and they usually kind of split. And I've been thinking about just removing retention time difference squared, but if you subtract, so that's about 16%. So it's also an important score, which tells me that my IRTs are probably trained pretty well. And then I can go look at the individual, scores. Intensity score, which was always a pretty good score for SRM, turns out to frequently not be the greatest score for DIA. This is the retention time difference plot. It actually has kind of too big a range. We should probably zoom the range in a little bit just because you don't really get to see the difference. This is the library dot product. Shape score is pretty good here. And then this coelution count is usually pretty good too. Yes. Negative contribution, it means it's going the wrong way. It's going the opposite way of what we expect. Yeah, I mean, usually it's because there's something that's nearly collinear, right? So the better scores are not collinear, like they add value. So I mean, you can certainly if you want, you could say like, and I have definitely done this, is like, oh, I want to get rid of the retention time difference squared, and then you could retrain the model. This is not going to apply the model, but it's good. It will retrain the model without. And so you could play around with this. That was in some respects, we consider Skyline also a research tool, and so we're trying to have people tell us like, oh yeah, I think I want to get rid of these scores because they're not useful. So you could remove them. In practice, they're not going to make much difference. We should have seen, yeah. So we see the importance of retention time difference go down, right? So it was accounting for like 30%, and then we had this negative percent. So they're kind of balancing each other. The weird thing about retention time, and that has worked fine. We've written papers, with that score in there. But the weird thing about it, the retention time difference square, we were kind of like, oh, it's a balancing score and it's helping even though it's going negative. But the weird thing about it is, if it is negative, it increases so fast that sometimes you can end up thinking things really far away are really good, because it's the square of the distance. And so it's somewhat confined by the range of chromatograms that you chose, but it has this weird quirk that, if it ends up negative, it could end up being a problem. So anyway, we'll cancel out of here. But yeah, you can certainly explore the feature scores, the p-values, the q-values. Q-values are all, are again, if we look at what proportion is below 0.01, which is our 1% false discovery rate, most of our q-values end up there. I mean, this is certainly a nice model. We don't even see really a big hump here, which is what you tend to expect when you've just taken a normal DDA library, right? So if you run DDA on your sample without any fractionation, without any special attempt to create a really huge library, you generally expect to be able to find the same things you found in DDA with DIA, only more reliably, as Rudy pointed out, I think, on the first day. So yeah, and certainly Brian's been talking about you're gonna find them more reliably. So actually, I think the paper that Rudy referenced from Roland Bruder at Biognosis showed that you might want to do DDA in a pooled sample and then do DIA on your quantitative runs the same way that Brian was describing for chromatogram libraries. All right, so we can just close this window. It's been applied. And then we can, we're running out of time here, but yeah, and then we can start playing with the data. We could set up the same kind of group comparison we had yesterday. We could go to peak areas CV histogram, and this one's kind of fun because it ends up being so strange. So who can explain why we have such a strange CV histogram? We have a bunch of stuff that's below 20% CV, but we have a whole bunch of, multiple humps here. Anybody have any ideas? Are we looking at just technical variance right now? Well, we've got both our A's and our B's, right? So we're looking at multiple conditions. And if you remember the tutorial, the conditions are human are actually expected to be essentially technical replicates. Yeast are expected to be twofold changing, and E. coli fourfold changing. So that, in some data sets I've looked at, the 3 humps are even more pronounced. But we can sort of get rid of those humps again by applying a group by. So we can say group by condition, and then now we're only looking at technical variance. We still see that there's a fair amount of stuff out here. It's not as sort of, I guess, as high quality data as we would like to see out of all the different peptides that we're measuring. We could I guess, oh, we can go to properties here and set a Q value cutoff of 0.1 or 0.01, I mean, and click OK. And then we can say that, oh, it's got to have, how many detections does it have to have? And we could say it has to have 2, or we could say it has to have 3, or, well, 4. There's not enough data. But yeah, so we can say 3, and then maybe things are getting a little bit better. Another thing we can do is normalize to medians. And that should make things even a little bit better. But I would say overall, you know, the technical variance in this data is not great. We would prefer to see something where we're getting more like 80 to 90% below 20% CV. So that's just some initial assessment of this data. We can check to see whether it's different in A versus B, and it's not really. And that's about it. So yeah, and now you can do a group comparison, and a volcano plot would be very useful here. Since we have so many samples. And that's it for the final Skyjam. Thanks for those of you who woke up early. We're going to take a 5-minute break and then come back with Rudy.